This is all of AP Calculus BC condensed in 2 pages. Unit 2, Limits and Continuity. To prove continuous at a point, we need 3 criteria. First, that f of a is defined, meaning it equals some value. Number 2, limit of x approaches a of f of x exists, and that is proven by showing that the limit as x approaches a on the left of f of x is equal to the limit as x approaches a from the right of f of x. If this is true, then limit of x approaches a of f of x exists. And number 3, you need to show that the limit of x approaches a of f of x is the same as the value of f of a. To prove continuous everywhere from negative infinity to infinity, you need to first prove continuous at possible discontinuity points. So if there's a piecewise function, you need to test every point where the piecewise function is breaking off and set the values equal to each other. And number 2, you need to state that the function type is continuous. For example, a polynomial function is always continuous. IVT, or the intermediate value theorem, guarantees a value c where f of c equals y in the open interval a to b, since f of x is continuous and f of a is less than y and is less than f of b. So basically, if y is between f of a and f of b, and y is within the open interval of a comma b, then there exists a value where f of something equals y. These are the derivative limit definitions. The first one is in terms of h. Limit as h approaches 0 of f of x plus h minus f of x over h, or the one with a where f prime of a equals to limit as x approaches a of f of x minus f of a over x minus a. This is the formula for Taylor form or linear approximation. You also use it. Y equals f of a plus f prime of a times x minus a. Unit 3 and 4 cover derivatives. First of all, a function is differentiable at x equals a, meaning the derivative can be taken at that point if it is first continuous at x equals a, and 2, that the limit of x approaches a from the left, the derivative of that is the same as the derivative of limit as x approaches a from the right. These are some common derivative of logarithmic functions. To take log b of x, the derivative of that will be 1 over x times ln b, and the derivative of something to the x power is b to the x power times ln b. These are 2 common limits. The limit as theta approaches 0 of sine something theta over something theta equals 1, and the limit as theta approaches 0 of 1 minus cosine something theta over something theta equals 0. These are 2 trig identities that you should know. Sine of a plus b equals sine a cosine b plus cosine a sine b, and cosine a plus b equals cosine a cosine b minus sine a sine b. The inverse derivative, or the derivative of an inverse function, is 1 over the original function prime on the outside with the inverse function plugged in at that point. The derivative of arc sine is 1 over the square root of 1 minus x squared, and the derivative of arc cosine is 1 over negative 1 minus x squared. Don't get that mixed up. And the derivative of arc tangent x is equal to 1 over 1 plus x squared. Next, we move on to logarithmic differentiation. Here's an example for that. This is when you have a pretty complicated something under the square root or something raised to a power, and you want to differentiate it. So you're going to take the ln of both sides and use the natural log properties where you can take the exponent and bring it down. So in this case, the whole thing is raised to the power of 1/2, so you can bring it down in front. So you have 1/2 ln of whatever is next. So you use the logarithmic properties to simplify the function, so it's easier to differentiate. And then you're going to differentiate both sides and then multiply by 1 over y, multiply by y to cancel that 1 over y at the end. There's another way to differentiate. This is limit manipulation. This is used when you have something that's an indeterminate form, or 0 over 0, or 0 to the power of 0. Basically something where you can't take the limit of, or you can't take the derivative of. So in order to find the limit of x approaches 0 of this value here, you're going to take the e of both sides, e to the ln of both sides, because that equals 0, so you're not doing anything. And then you're going to rewrite the exponent so that you bring the e down and the limit goes up, and then you can simplify again using the logarithmic properties, and then you can solve for the limit. For application of derivatives, important things to note are that acceleration and when velocity and acceleration are in the same direction, or they have the same signs, whether it's plus or minus, then that means that the particle motion is speeding up, and if it's opposite signs, that it's slowing down. Average velocity, you're taking basically the average rate of change of the position, and for average acceleration, you're taking the average rate of change of the velocity. Extreme value theorem is if f of x is continuous over the closed interval of a comma b, then it has at least one max and one minimum within that interval, and the critical points and the endpoints can also be absolute max or minimum, so make sure to test those points as well and show the integrals for every q. And then the mean value theorem, or MVT, is first you state that f of x is continuous over the closed interval a to b and differentiable over the open interval, and if that's the case, then the function has a value of c in a comma b where f prime of c is equal to the average rate of change. And Rolle's theorem is just one type of MVT, where if f of a equals f of b, then basically the average rate of change is 0, so the derivative at some point c within that interval must also be 0. The first derivative test is for at critical points, and you're trying to find if a value is a relative minimum or maximum. If the function changes from increasing to decreasing, or the derivative is changing from positive to negative, then at that point there's a local max, and vice versa will be a local min. The second derivative test is also to find local maximum or minimums, also critical numbers, but if f of the first derivative is 0 or dne, and the second derivative is negative or less than 0, that means the function is concave down, then at that point it must be a local maximum, and opposite will be a local minimum. Points of inflection. If f double prime equals 0 or dne, then that makes it a possible point of inflection. That doesn't mean it has to be a point of inflection, but if that's applicable and f double prime or the second derivative also changes from positive to negative or negative to positive, then that point is a point of inflection, and that could be a local maximum or minimum as well for the first derivative. Moving on to Unit 5/7 of integrals, we start with the definition of a definite integral using the limit of a Riemann sum. Limit as x approaches infinity of the summation from sum k equals 1 to n of f of a plus b minus a over nk times b minus a over n, that is equal to the area under the curve, or the definition of an integral. The fundamental theorem of calculus. The first one is that the integral from a to b f of x dx is the same as the antiderivative from a to b, and the derivative of an integral from a to x is just f of x. So the derivative and the integral are inverse functions, and if we're taking derivative but instead of an x or an a there are functions there, then we apply the chain rule there. For net change in position, we just take the integral of the velocity from a to b, and that is equal to the change in position from the position at A to the position at B. And the net change in velocity, we would take the integral of the derivative of the acceleration. For total distance, we just do the square root of the velocity, take the integral of that, and if it's not a calculator portion, then you're just going to find the zeros and split up the integral from every point that is a zero and do absolute value bars over each. Trig integration, some important identities are here. Sine of 2x is 2 sine x cosine x, and cosine 2x is cosine squared x minus sine squared x, and the power reducing rule is also important, especially for later in the polar unit. The sine of x squared is y minus cosine 2x over 2, and cosine squared x equals 1 plus cosine 2x over 2. For rate in, rate out questions, the total amount, which you set equal to some function, for example, a of t, is just the initial amount plus the integral of the rate in function minus the integral of the rate out function from a to b. And the average value of a function is 1 over b minus a times the integral of f of x dx, and that should give you the same unit as the function f of x. For the area and volume, for integral between two curves, you're just basically taking the derivative, the integral of the top minus the integral of the bottom, or vice versa if it's left and right. Then you do the dy. And something important to remember is that the integral of the area is the volume. For disk and washer, if the function is touching the axis of rotation, in this case like that, then you can just do the volume is the integral from a to b of pi times f of x squared. And for washer, you're going to do pi OA, where O is the outside function here. Oh, that's terrible. O will be the outside function, and A will be the axis. So outside function minus the axis squared minus the inner function here minus the axis squared. For arc length, we have two functions depending on dx or dy, but basically the integral from one point to another of the square root of 1 plus the derivative squared. And for cross sections, these are all the shapes, and all of them use some variation of the integral from f of x minus g of x squared, and then you're just going to attach some coefficient in front of it depending on which cross-sectional shape it is. Unit 8 or 9 is differential equations and slope fields. So for differential equations, you probably will be asked to find the function using the separation of variables. So you're going to separate the x and y's, integrate with a plus c on one side of the function. So for c, isolate y equals f of x, and pick either plus or minus by plugging in the original condition that will be given to you. This is one example here. For logistical growth, the important things you need to remember are basically just these formulas. The derivative of logistical growth functions can be seen in two forms, but mainly the main one is dpdt equals kp times 1 minus p over m, where p is the population and m is the carrying capacity. Something important to note is that the inflection point happens at m over 2, so half of the carrying capacity is when the function is growing at the fastest rate, and the solution will be m over 1 plus a e negative k t to the power of negative k t. This is Euler's method. Basically, you're using the tangent line approximation of the Taylor form, but you're doing that approximation over and over again, where you plug into the previous tangent line and you do it again until you get to however many step sizes you need. Unit 10 is parametric polar and vectors. So parametric curves or equations are in the form of a parameter t. So you'll have a function x equals f of t and y equals another function of t. To find the dy dx, or the derivative of that function in the xy plane, you're going to do dy dt over dx dt. And the second derivative is just the derivative of the first derivative, and divide that by dx dt. That's very important. For arc length, or the total distance, that will be a little bit different from the previous arc length equation, but you're taking the integral from a to b of the square root of dy dx squared plus dx dt squared. Wait, that's wrong. That should be dy dt squared plus dx dt squared. And the speed is again the absolute value of the velocity. And you're doing this basically the same arc length formula, but without the integral, so it's just going to be the square root of dy dt squared plus dx dt squared. For the position function, it's basically the same. You're taking the initial position of either the x or the y in terms of t, and the integral from one point in time to another of the function either x prime of t or y prime of t. For vector functions, you're basically writing them in terms of a vector, so you use these brackets here, and you're going to do one side is going to be the x and one side is going to be the y. The slope of the tangent line is the same. Important to know the particle is at rest in particle motion when both the x prime of t and the y prime of t equals 0. And again, if the particle is speeding up, if they have same signs, the acceleration and the velocity, and they're slowing down if they have opposite signs. Polar coordinates are like xy, but instead of xy, it's in the form of r comma theta. To convert rectangular to polar, you can use x squared plus y squared equals r squared, or tangent theta equals y over x. And to convert polar to rectangular, you'll use x equals r cosine theta and y equals r sine theta. For polar derivatives, it's basically the same thing as the parametric ones, but instead of t, you replace theta. So you plug in the r equals f of x, or f of theta that they give you, and then x equals, you plug in r cosine theta, y equals r sine theta, and then you use it in the same way to find the derivative of both dy d theta and dx d theta, and dy d theta divided by dx d theta is dy dx. These are the classic polar curves. Make sure to know the forms. Most common one is probably limaçons and circles and roses, where you might be asked to find the area of a polar curve. To do that, first it might be helpful to graph the polar curve. So you first find the polar zeros by setting r equals 0, and find the max values where the theta where r is at its max. And to find the area of the polar curve, the formula is 1/2 the integral of r squared d theta. Some helpful tips is you can find the area from pole to pole. So you find where the polar zeros are, and you find the area from pole to pole. That's going to be your bounds A and B for the integral. You can only use 0 to 2 pi for whole limaçons. The other ones, you need to find the polar zeros first. Power reducing will be useful, and you can also use half and double petals and loops, or the symmetry. And to interpret dr theta, if theta increases and r is positive, then r is moving away from the pole, and if r is negative and dr theta is positive, then as theta increases, r is moving closer to the pole, and the value of r is decreasing. Finally, we have unit 11, and that's series. So first, the limit of a sequence, which is the terms within the sum of all the terms of the series. If the limit of n approaches n of the nth term equals a number, then that's converging, and if the limit is d/n/e, then that's diverging. And so that's a sequence, and when you add up all these sequences, that becomes a series. The Taylor series approximation can be found using f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared, etc., etc., etc. And this is the final form. For Maclaurin's, you're just basically plugging in 0 for a. So you're finding the first term is going to be the value of the function at 0, and then the first derivative times x, and the second derivative times x squared over 2 factorial, etc., etc., etc. These are some common Maclaurin's to memorize. So sine of x is approximately x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. Cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. E to the x, you can remember as e equals everybody. So 1 plus x squared over 2 factorial plus x cubed over 3 factorial, basically just every term. And for another one to remember is 1 over 1 minus x, and that's just basically e to the x, but without all the factorials on the bottom. The Lagrange error bound, this is the formula for that. You first take the next derivative, the max value at x of the next derivative at either x or a over n plus 1 factorial times x minus a to the power of n plus 1. And that is the error bound. So the difference between the approximative value minus the actual value is going to be less than or equal to the error bound. Now here are all the convergence and divergence tests of a series. First, you start with the geometric series, where if there's a common ratio and the ratio is less than 1, then we know that the series converges because of geometric series. They always converge, and the sum of that is the first term over 1 minus the ratio r, and that's the only type of series where we can know what it converges to. For the other types of convergence or divergence tests, you only know if they converge or diverge, but not what the number is. Next, we have the n terms test, which is usually the first one you should use. The limit is at n approaches infinity of some of the nth term. If it's not 0, then it's divergent, and if it's not, we don't know if it's convergent or not, but it's inconclusive. The ratio test. Basically, we're taking the limit as n approaches infinity of the absolute value of a to the n plus 1 over a to the n, a of n, and if it's less than 0, if it's less than 1, it's converging. Greater than 1 is diverging, and if it's equal to 1, it's inconclusive. So you can also just set the absolute value bar less than 1 and solve for x to test the endpoints to find the interval of convergence. And if the value is 0, then it's converging everywhere. And if the value is infinity, then it converges at the center only. The interval test. You need to show all these steps for the f of q. First, set if a sub n equals to f of x. Say that f of x is continuous from 1 to infinity. F of x is greater than 0 for x is greater than 1. F prime of x is less than 0. Basically, you're showing f is continuous, positive, and decreasing. And you're going to find the improper integral. And if the integral is converged to the number, then it's converging. And if it's infinity or d/e, then it's diverging. P-series test is the series of when the n term is 1 over n to the power of p. If p is greater than 1, converging, less than 1, diverging, and if it's equal to 1, it's also diverging because of harmonic series when it's just 1 over n like that. Direct comparison test. Again, you have to show first that a is positive, so greater than 0, and then you're going to write compared to b sub n, and just find another series that you want to compare to, and write if b of n converges or diverges and state the reason why. And if a sub n is less than that, then both of them converge. And if a sub n is greater than b of n and b of n diverges, then both of them diverges. Similarly, with the limit comparison test, first you show that a sub n is positive compared to b sub n, and state that the series b sub n is converging or diverging. And if the limit of a sub n over b sub n, if that ratio comes to a number, then both of them either converge or diverge. Alternating series test. First, you show that the series alternates. Then a sub n is greater than 0. Then you have to show that the next term is always less than the previous term. And you can do that in two ways. Either you do a sub n plus 1 minus a sub n is less than 0, or you do the ratio that a sub n plus 1 over a sub n is less than or equal to 0. And then finally, you show that the limit is n approaches infinity of a sub n equals 0. And if all those four things are true, then a sub n, the series converges. Alternating series error bound is similar as Lagrange error bound, but first, this is only for alternating series. And you first have to show all these four steps to show that at first the series converges by alternating series test. Then the actual values minus the predicted value is going to be less than or equal to the next term in the alternating series. Finally, for absolute versus conditional convergence, this is when you test endpoints as well. Or no, sorry, you use the alternating series bound to test endpoints. And for absolute versus conditional convergence, if the series with absolute value bars converges, then it's converging absolutely. And if the series converges without the absolute value bars, but with the absolute value bars, it diverges. So it only converges if it's alternating. Otherwise, it wouldn't. Then the series converges conditionally. So that's all of AP Calculus BC.